Yeah, so today I'm going to give a talk on how our thoughts have evolved over the last couple of years and a pretty unique design that we have since put into place. All right, so yeah, we'll give a very high-level overview of RFQ. I think it's a much more well-understood system at this point. How to think about DEX quotes, dig into a bunch of data, and then we'll actually talk about our design. All right, so quick primer on what RFQ is. So RFQ allows you to trade peer-to-peer against professional market makers. So user comes in, they request a quote, what's the best price you could give me for, if I want to make a trade of this amount. All the market makers respond with their best quotes, user agrees, and submits a transaction. RFQ has some really nice properties from an MEV standpoint. So trades are always, they always happen at a predetermined price that is fixed in the signed quote. Therefore, they always have zero slippage. No MEV is possible when trading this RFQ. The quotes are tailor-made for the taker as well. So the order format actually specifies the taker's address as the only address that's allowed to fill the order. Therefore, they can't be front-run or anything like that. And yeah, back when I did a presentation a couple of years ago, RFQ was making up roughly 40% of volume through 0x. So yeah, just a reminder for those who aren't too familiar, 0x is a liquidity aggregator. So it routes between RFQ and all the other on-chain liquidity sources. So 40% of trades were MEV free, but if you take that a step further, it is not actually enough, right? Like if we're comparing an RFQ quote, which always has zero slippage, versus other quotes that potentially have slippage, you can't actually really treat those quotes equally. And yeah, I think most people don't really understand this, but yeah, AMM quotes are kind of bullshit. Like they don't really mean too much. The expected value of a quote is going to be less than the quote itself. They don't account for any market action, anything that's happening in the mem pool, anything that's happening in private mem pools. Don't account for any hidden fees like positive slippage. And yes, you thought you were done with Tom memes, but
that's from 2019.
That is from 2019. So yeah, and yeah, another way to think about this is that what people think of as market orders in decentralized exchanges are really basically limit orders. So they're currently kind of framed as, okay, I'm going to make a market order at this price, and I'm willing to pay up to some other price. But if we rephrase that, what you're really doing is you're placing a limit order at that second price, and you think maybe you could get that first price, but there are no guarantees around that at all. So we can do better. So we seeked out how do we address this problem? How large is the problem? First of all, since we are an aggregator, we have a lot of data, right? We see all the user quotes. We can try to map those to the actual trades that are settled on chain, and we can compare the two and have a lot of data on realized slippage, across every single token, basically. So this is sorry, let me just describe this. This is a histogram of realized slippage, and the scale is normalized, so don't read too much into that. But you can see on the right-hand side, the positive slippage follows the power law distribution. So that's when your realized price is actually better than your quoted price. That is possible to happen. But the negative slippage on the left-hand side is pretty interesting. We see these spikes where users are realizing higher than average slippage, and we think that is happening because those are the levels which users are setting their slippage tolerance. So I will show you more data proving that is actually happening. Here's another chart showing slippage exhaustion across all trades. So this is a metric we created, which is the realized slippage divided by the slippage tolerance of trades. So if you set your map slippage to 10 basis points and you realize 9 basis points of slippage. That's 90% slippage exhaustion. And it's also more or less looks like a power law distribution until the very end, and you see there's this huge spike where a larger than average amount of trades are actually hitting very close to that max slippage tolerance. So what's happening there is that MEV searchers are basically treating these as limit orders. They are capturing as much of that delta as they can. And we can also see that this problem gets worse as trade sizes get larger. So the likelihood of you hitting your max slippage for a very large trade is going to be something like 14%. And then we'd also see, this kind of quantifies in dollar terms how bad the problem is. We can also see that slippage trends up as trade sizes get larger for all of these major pairs. So we have all this data. How can we actually put this into use and help out users? So we created this feature called Slippage Protect, which I think is a pretty unique design. I haven't really seen anyone else do anything like this. But the idea is to essentially make the aggregation routing MEV-aware. So we have all this data on what is the average slippage for every single given liquidity pool, token pair, and trade size bucket. And then when we are routing through all of these sources, we can actually essentially penalize certain routes if we think that they are going to realize slippage, and route people towards things that will realize less slippage. So our hypothesis is that by factoring in average slippage, users should have higher quote accuracy. It should decrease their realized slippage, and overall should improve execution quality for users. So I kind of think of this as like it's like an order flow preprocessor. So you're optimizing the route to minimize the MEV that is extractable after the fact. So did it actually work? Well, you could see the difference in orders that use the Slippage Protect feature and orders that do not. So it's optional for users of the API. So some people use it, some people don't. But we could see on the right-hand side that the trades that are using Slippage Protect actually realize pretty significantly less slippage on average than those that do not. So what are the implications of this feature? Users are going to get improved accuracy of quotes. It's going to end up routing more volume through liquidity sources that do not have slippage or have less slippage. Today, that's pretty much just RFQ with a zero slippage, and also some order books has zero slippage. Trades on average should have better execution, but one limitation is that does not mean that every single individual trade will have better execution. It's actually possible for a trade to end up having a slightly worse price, but on average, it should be much better. And like I mentioned, it's basically an order flow preprocessor, so it should decrease the total MEV that is possible to take out from searchers. It's also just automatic for users. They don't need to use custom RPCs or anything like that. So, as Tom mentioned with MetaMask, there's no way to force your users through a private mempool. So, especially if it's a non-technical user, and I assume most people don't even know what a private mempool is. This is really going to help out that type of user. One limitation is that if you are using a private mempool, this does not perfectly account for that, although it should be somewhat reflected in the data because the data set is using transactions that went through both public and private mempools.
So I guess two questions. One is it's a bit of a straw man to be like, oh, the quoted price of the CFM is whatever, and therefore that should be the expected price. I don't think anyone actually thinks this, and it's kind of weird to say we expect slippage from CFM, but not from an RFQ. No one's going to give you the same expectation price for CFM. Right? no one's to be like, yes, you can trade your like million ETH for exactly the market price. And in our period, right, like that's fundamentally the point, is like there's only a certain amount of liquidity that you can get from market makers. So it's maybe a less explicit version, I would say, than kind of the trading curve that you get. So I don't know if you have any thoughts on that, but
Well, I think there are actually a lot of products out there that do treat quotes equally, right? Like most aggregators in their routing algorithms, they're going to look at all of them the same. Meta aggregators that compare multiple aggregators, they're going to look at quotes in exactly the same way. So,
so I actually think that's also great because the routing problem over CFMs is convex, so you can just solve it, right? I can just like give you a very fast algorithm that can solve it for like 10,000 pools in like 100 milliseconds. So I actually we have code online for it too. So, but how does that compare with the slippage? Like you're removing certain markets that have slippage, we can just solve the problem optimally, like in the first place. Like why not just solve it and then post it on chain? Does that make sense? Sorry, I can also rephrase the question.
yeah, you have to read.
So I think the way to, so what you're doing is you're saying like, look, and let me make sure I'm understanding this correctly. We're going to remove pools for which there's a lot of observed slippage.
You don't remove the pools, you simply penalize them for the expected slippage amount.
Sure. Okay. But the point is, okay, what are you doing? You're saying like, look, I'm going to give you, you give me a bunch of ETH, and I'm going to give you a bunch of Shiba, right? And I'm going to guarantee that in fact the amount of Shiba that you get out is maximized. That's ideally what you're trying to solve, right? That's the hopeful objective. So my claim is that that problem is actually efficiently solved to global optimality.
Okay.
So why not just do that instead of the heuristic where you penalize pools for slippage?
How do you solve it?
Yeah, actually you should check it out. Look up cfmmrouter.jl. And there's a very fast
I think the problem is that with a CFMM, right, the stick and change out money.
Exactly.
Sure. Yeah, but that's why you have, like, you're giving me a dark pool in the first place, right? Why not just like submit the thing, the order, and then have it be executed at something that you can pretty much guarantee it's going to be accurate. Right. You have the same problem even in the case of like submitting orders through many like.
The only way to kind of cap your slippage on a particular pool is via the limits for that pool, right? I say revert this transaction on DEX. If any slip comes up under that, then you're going to have a reverted transaction, which is arguably even worse than having my trade get a slightly worse execution.
But you'll already have this even in the system too. Right. Like the point is that by definition, solving the optimal problem means that you're already like considering the slippages in the first place. Like that's what it means to optimally solve it. Like you're already doing that by default.
But how do you optimally solve it with like all these unknown actors interacting with liquidity pools?
Like if you factor in the worst possible, then you're going to bias way more toward
You can do it in expectation, you can do it probability.
Which
so
is
it's
that's exactly the same.
is it?
Yes.
Yeah.
So okay, so when you say slippage, you're talking about like some sort of like realized model of probability over like such a percent you get. And like why is there such a difference in different pools? You know, is it just like certain standard tricks just like happen to live in certain pools and like bite the people who like go across it? Is that or am I?
I mean, I think it's not that much different across AMMs. You know, it probably depends if it's like, you know, more like UDP2 or a tick-based AMM. But yeah, I think generally it's not.
Right, but it seems to be more of a property of liquidity rather than a property of like that particular pair. So then what I'm saying is you can just have a model for that in the first place, not like the slippage-based model. It's like you already know like what the slippage is going to be ahead of time, right? That's the whole point. So I don't know. Maybe I'm not quite understanding what the mechanics of this like slippage based thing.
When you say slippage, do you mean price impact?
No.
Slippage, or you mean like total amount of liquidity,
Oh.
whatever.
I will explain in my
Price
slide.
impact is very different than
Okay.
slippage.
Yeah, that's what I hear you saying. That's what the TFM giving you a defined amount. That's price impact.
Yeah, here, I'll define it for you. This is Dan, right?
Yeah.
I'll define it for you as the K in front of your trading function. Does that make sense? There you go. That's liquidity for you.
I think you're more mathematically inclined than I am. But yeah, it's interesting. It'd be interesting to look into it.
Oh.
Okay.
Any questions?
That's a good question. How do you think about like, is it like sort of market-based approaches to sort of pricing like cow swap versus like 0x?
I think I think for this specific model, it is like largely stackable with other models. I don't think it's like one or the other, but yeah, I think like internalization type models are pretty interesting and proprietary.
I have a question. When you do the analysis of slippage, like on lower slippage orders, you have like a higher chance of your order reverting because it's like cheaper for someone to make your order revert. Did you like incorporate like your multi-block fill? Like if users get reverted and they submit the same order and over again and they keep reverting, like do you account for that or do you just assume that they get filled in the first block?
That's a good question. We do not do that, although we have thought about it. It's a little, I mean, you can measure like lost gas costs. You can't really measure lost time that well. And overall, I'm just not sure if we can support the squeeze, but it is like a potential optimization.
Yeah, I think for the average retail user, it doesn't really matter, but for like wallets that have been tagged with informed flow, the information you give up with like I just suggest the fact that it's a weak flow from the ANM actually really matters. That you don't have any strong guarantees you'll get the first fill, and that you can effectively be censored from above. Like essentially, like large wallets that have are perceived to have information